Okay, in this segment we're going to be looking at the differential mode gain, of the current mirror diff amp. I'm going to use node fixing to do this. So our current mirror diff amp looks like this. There's a diff pair. A couple of PMOS current mirrors. So we have VB, MB, M1, M2. And we're going to have a common mode input here, common mode input here, M3, M4, M5, M6, and an NMOS current mirror, M7 and M8. We have our output voltage V out. And what we're going to do is the same thing we did with our 5 transistor diff amp. We're going to apply a test voltage source to the output, whose value has been pre-adjusted to match the quiescent operating output voltage. And that quiescent operating output voltage we argued last time is going to be the same voltage as is on this internal node here, which we called V7 last time. And at that point, there will be no current exchanged with the voltage source. And then what we're going to do is apply a little delta VDM to one side of the diff pair, and we're going to pick M1, and we're going to compute what is the delta I out that we get. Due to that delta VDM. And that'll allow us to calculate the transconductance gain of the circuit as a whole with the output voltage held fixed. That's half of the node fixing calculation. And so let's do that. So it turns out that we don't need to consider any of the early effect resistors anywhere for this particular calculation. And I'm hoping that I'll be able to explain to you sort of at least a heuristic for, or at least the heuristic that I typically use when I think about a circuit and doing an analysis like this of where we need to account for the early effect during which phase of the calculation. But I'm not going to do that at this moment. So what we're going to do is apply our delta VDM, and that's going to create an increase in the current flowing through this transistor M1. We'll call it delta I1, and we have to figure out what happens to this delta I1 as it propagates its way through the circuit toward the output. Well, one thing that it's going to do is it's going to flow out of the M3, M4 current mirror. So there's an extra bit of input current to this current mirror, which gets mirrored by M4. And that's going to be all coming out as output current for the same reasons that we discussed with the 5 transistor diff amp. Namely, the only place for it to go with no early effect resistors would be to the output voltage source. If we did have early effect resistors here and here on M6 and M4, the voltage is being held fixed across those resistors, and so they can't change the currents flowing through them. And so the only place that that extra current has to go is into the voltage source. Yet a third way of looking at it is the idea that it sees a current divider and it goes for the highest conductance path or branch, and the voltage source, the ideal voltage source, has basically an infinite internal conductance, incremental conductance, and so all of the current will flow into the voltage source from that point of view. So that's half of what the delta I1 does. Delta I1 also flows out of the source of M1, and then we have to figure out what happens as that flows onto the common source node. Well, it can't go down into the MB transistor because that's the drain of a saturated transistor, and so it must flow up the source of M2. Right? This is just saying, once again, that the current flow through M1 and M2 is a zero-sum game. They sum to a constant IB, and so if we increase the current in M1 by some delta I1, we also have to reduce the current flow in M2 by the same delta I1 in order for them to sum to a constant. And so we can represent that reduction in I2 as a small increment flowing against the quiescent current flowing in M2. And so that current's going to flow out of the drain of M2 and into the current mirror, M5, M6. And that current is going to be mirrored by the M6 current mirror, or mirrored by M6 in the output of that current mirror. It's going to flow out of the M7, M8 current mirror, be mirrored by M8, and that's also going to have to come out through the output of the circuit. And so delta I out, just like the case of the 5 transistor diff amp, is going to be 2 times delta I1. And we can write delta I1 in terms of the change in the gate voltage here by using that result that we looked at last time as well, where we have a source degeneration of a saturated MOS transistor, and so we have 2 times little gm1 times delta VDM divided by 1 plus GS1 times the incremental resistance that's connected down here, and that's going to be 1 over GS2 but again GS2 equals GS1, and so this will just cancel and become 1 plus 1. So this is equal to 2 times GM1 over 2 times delta VDM. 2's cancel, and so we have the GM of the whole circuit, which is delta I out over delta VDM, is just going to be GM1. Just like it was with the 5 transistor diff amp. Shouldn't be a big surprise. The output current here is just I1 minus I2, the diff pair differential output current. And so just like it was with the 5 transistor diff amp, and so the GM we might expect to also be the same. And so that's half the calculation. So to do the other half of the calculation, we turn off our input voltage source, and that takes away these current increments. So we can do this without damaging the circuit too much. That's not too bad. And what we're going to do is we're going to apply a little delta V out and see how much current goes back in to the circuit to probe the incremental output resistance of the circuit. Now here, we're going to need to have an early effect resistor for M4 and for M8, okay? And that's simply because if we were to consider these as current sources, I out would be 0. The change in I out would be 0 for a change in V out. And we would conclude that the output resistance is infinite, and that the gain is therefore infinite because we have a finite transconductance times an infinite output resistance, and that would be unrealistic. And so any finite output resistance contributed by the early effect is going to be sort of a dominant factor in determining what the gain of the circuit is. And so we're going to have an RO8 in parallel with M8. We're going to have an RO4 in parallel with M4. And we're going to use source splitting, voltage source splitting. So we're going to split this voltage source into 4 replicas, one connected to each of the things connected to the voltage source. So we've got the early effect resistors and the 2 drains. Now we're going to use superposition to consider the effect of each replica source voltage change in turn. And so splitting the output source would look something like so. We're interested in the total current flowing back through this bundle of 4 wires, delta I out. And so we have V out, V out, V out, V out. We'll call this 1, 2, 3, 4. And we're going to be interested in applying our delta V out to each of these 4 replica sources in turn, and seeing what the components of delta I out are due to each of those. And so recall our numbering convention is that delta I out sub ij is the component of delta I out in branch I due to replica source J. Okay, and so there are 16 possible components of delta I out. 4 branches, 4 replica sources. We could have, in principle, 4 for each of the replica sources. But in practice, we're going to find, just like we did with the 5 transistor diff amp, that most of these are going to be 0. And that matrix of components, if you want to think of it as a matrix, is going to be very sparse. And so delta I out is equal to the superposition of all these components. And so let's apply our delta V out to branch 1. Well, we're talking to an early effect resistor, and if we change the voltage across a resistor, it's going to change the current. And so the current delta I out 1, 1 will be non-zero. And we can write that down as delta V out over RO4 just by Ohm's law, or incremental Ohm's law. Now that current, when it flows out the other side of this resistor, just goes to the power supply, and it doesn't change the voltage on the source of M4 at all, so it doesn't change the amount of current flowing in M4. And so there's only one component due to replica source 1, just because there's no other currents excited, or there can't be any other currents excited in the circuit as a result of this current flowing back into the output voltage, or into the power supply voltage source. It doesn't affect any gates of anything else. It's just, that's it. And so 3 out of those 4 possible components due to replica source 1 are 0. We march down to replica source 2. And we take this one away. Well, here what are we talking to? Well, we're talking to the drain of an ideal PMOS transistor that's saturated. And so we've encapsulated the early effect of this transistor in RO4, taking that into account separately. And so that there is no current flow into M4's drain due to the change in replica source 2. And that's also not connected to anything else, and so has no other effects in the circuit. And so all 4 components due to delta V out on branch 2 are 0. So that's 7 out of 16 components so far of the 8 considered so far that are 0. Well, if we move on to branch 3, here we're talking to the drain of M8, ideal transistor. We've encapsulated the early effect in M8 in RO8. That's separate. And so this really is an ideal transistor that's saturated. And so the change in the drain voltage does not excite any more current flow into M8. And so there is no delta I out 3,3, and in fact no delta I out anywhere else either. And so we've now considered 12 out of the 16 components, and 11 out of those 12 components have been 0. We move on to branch 4, and here we're talking to a resistor. Okay, and so there is a delta I out 4,4. And just like our delta I out 1,1, that's given by incremental Ohm's law, delta V out over RO4 this time. And so we have delta I out 4,4. But in this case, also that just flows into ground, doesn't affect any other current flow in the circuit at all, and so does not have any other components of delta I out, or does not excite any more components of delta I out. And so this is our complete delta I out. Of the 16 possible components, only 2 are non-zero, and 14 are 0. And this is actually fairly typical of the way this works out. So R out which is basically delta V out over delta I out. So we factor out the delta V out, we have delta V out times 1 over RO4 plus 1 over, oh, it should be 1 over RO8, shouldn't it? I got my branch 4 confused with my transistor indexing. RO8. So we get delta V out times the quantity 1 over RO4 plus 1 over RO8. If we move that downstairs on the other side and bring the delta I out downstairs underneath the delta V out, we're going to have 1 over RO4 plus 1 over RO8, which is just RO4 parallel RO8. And so the differential mode gain, which is just the product delta V out or delta VDM, that's just going to be GM1 times RO4 parallel RO8. This is just exactly the same sort of result we got for the 5-transistor diff amp. The transconductance gain of one of the diff pair transistors, actually they're both the same, so it's either one of them, times the parallel combination of the output resistances of one NMOS and one PMOS that are in the output, connected to the output node. And this calculation, even though the circuit has more transistors in it, is actually quite a bit easier than the 5-transistor diff amp was, because in some sense these extra pair of current mirrors sort of decouple the output node from what's going on here in the diff pair. And so we don't have to consider any current injected onto the diff pair common source node and how that kind of splits and comes back out, and there's none of this canceling of two components of delta I out. That's really nice. It also says that this should have basically the same sort of gain as the simple 5-transistor diff amp does in terms of, for a given bias level and a given transistor length and say early effect resistance and things like that, early voltage parameter, they should have comparable gains. Okay, so if I have a 5-transistor diff amp and a 9-transistor current mirror diff amp, and I have the bias level set to be the same place, and the transistors are matched between the two, the NMOSs match the NMOSs and the PMOSs match the PMOSs, I should get basically very comparable differential mode gains, and also common mode gains. So that is the whole calculation. You might be wondering to yourself, why aren't we using node fixing to figure out the common mode gain of these circuits? Why are we using some other method for doing that? And the answer to that has to do with the sort of approximations that we're making when we neglect the early effect. So for the GM calculation, for instance, we didn't account for the early effect anywhere. And if we were to put if we were to put an early effect resistor in here with a bias or something like that, and we were to say, okay, well, suppose we had our delta I1 coming down here. It sees this two-way current divider. Some of it goes this way, and some of it goes this way. And we can write down a current divider ratio, which is going to be something like the amount that goes this way is 1 over GS2. I'm sorry, it's GS2 divided by GS2 plus 1 over ROB. And we can turn that into a GS2 ROB over GS2 ROB plus 1. And to the extent that GS2 ROB is much bigger than 1, the ROBs would cancel if we neglect the 1, and we'd be left with what we assumed was the case before without the ROB. Unfortunately, the level of approximation that we're making with that kind of consideration might be somewhere in the range of like a 0.1% approximation to, let's say, a 1% approximation. Let's say if the intrinsic gain is somewhere between 100 and 1,000, that would correspond to the kind of level of approximation that we're making as we chase these current increments around the circuit. Same could be said for having early effect resistor here in parallel with our current mirror. That extra resistor in parallel with the current mirror we can think of as stealing some of the current, a small fraction of the current from the input of the current mirror, and so that would result in a slightly less amount of current being mirrored by the current mirror. Unfortunately, if you think about how much smaller the common mode gain is than the differential mode gain was something like 100 or several hundred. And the common mode gain was something like 1 over 100, or maybe 1 over several hundred. And if that's the case, then what we're talking about here is if we have a mixture of sort of common mode currents and differential mode currents that we're considering, those common mode currents are like on the order of 0.01%, as large as what's going on in the differential mode. And so the kind of approximations that we're making customarily to figure out the differential mode gain conveniently are things that basically completely swamp out or render invisible any of the common mode behavior that's going on. And so if you try to only selectively account for things like the early effect when you're doing the common mode calculation, you wind up getting the answer wrong. You get something that's in the right order of magnitude, let's say, but it's very easy to be off by a factor of 2, 100%, or more. And so it does turn out, I did try this one time many years ago, by doing everything out, let's say for the 5 transistor diff amp, using node fixing ideas and not making any approximations until sort of the last possible minute. You do get exactly the results that we've shown here for both the differential and the common mode gain. But unfortunately, the expressions would be such that if you were to start to write them out, you would have to wrap around probably 2 or 3 lines, turn the paper sideways, and the expressions kind of go into the 2 or 3 lines. And so it's definitely not a fun thing to do. It's not impossible. You have to be a little careful, but it's definitely not the kind of thing that you would like to be doing. And it's not the kind of thing that really brings a lot of insight. And so, when you're looking for something that's a very, very minute effect, you have to be careful about the kind of approximations that you're allowing yourself to make and how good they are. Anyway, so that is the differential mode gain of the current mirror diff amp. The next thing I'd like to do is to do something that is very similar to this, and we're just going to sort of reuse most of what we just did. So if I can take away these little current increments and reconstitute the circuit, I want to think about what would happen to this differential mode gain that we just worked out. What would be different if we stuck a capacitor on the output of the circuit? As you're actually doing in lab this week. All right, so we're going to go through this a little more quickly. And we're interested in doing the node fixing thing again to figure out what is the differential mode gain. So we fix V out. And we're going to be interested in asking ourselves, what's different about this case with that capacitor there? Well, if we apply our delta VDM to M1 again, we again excite our delta I1, and that's going to flow again through all of these current mirrors toward the output here. It's going to flow out of M3, M4, so this is delta I1, this is also delta I1, and we're interested now in the delta I out that flows out of the circuit. Well, to here, the currents are exactly the same. We're going to have 2 delta I1 flowing out of M4 and M8. just like we had before. Question is, does this capacitor do anything to steal some of that current from the output voltage source? Now, if we were actually in class, I would probably pause at this point and ask you guys to think about that. And so if you want to think about it for a couple minutes and see if you can figure out the answer, I'll wait a couple seconds here. You might want to pause. Of course, the answer is no, it doesn't. Because we're holding the voltage across this capacitor fixed by this voltage source. The current through the capacitor, right, IC would be C times, or C out here in this case, times dV out dt. Well, what's dV out dt if V out is being held fixed with a voltage source? That's equal to 0. Volts per second if we have to put units on it. And so that's equal to 0. And so delta I out is just 2 delta I1, just like it was before. Just like we said that if we had early effect resistors here, because the voltage has to change in order for there to be a change in the current flow through the resistors, and we're holding the output voltage fixed, not allowing the voltages to change, the early effect resistors can't admit any current, or can't change the amount of current flowing through them. And so there's no delta I flowing through them. Just like that, with a capacitor, when we're holding the voltage across it fixed, there's no dV out dt, there's no current flow through the capacitor. Okay? So here, delta I out is still 2 delta I1, and the GM of the circuit as a whole is still GM1, little GM1. Okay, so that part of the calculation has not changed at all by the presence of that capacitor there. And so now we have to go back and ask, how about the output, the R out, or more generally, the Z out, the impedance, the output impedance of the circuit. Take away our current increments. And we're going to probe the incremental output impedance of the circuit by wiggling around the output voltage source, and we could consider this delta V out here to be a sinusoidal excitation with some small amplitude at some driving frequency, and ask what is the delta I out, which will be a sinusoidal, small amplitude sinusoidal current in this case. How does that depend on V out? And then look for the ratio delta V out to delta I out. Well, we could split this with put our early effect resistors in here again, RO8 and RO4, and split now into, instead of 4, into 5. But since we already did split the output of the amplifier by itself into 4 and use source splitting, we can get away, and we know what the output resistance is of the circuit here without the capacitor. We can get away with splitting it only into 2 pieces, or into 2 replica sources. So we're going to keep these 4 together, and we're going to just split into the output of the amplifier and the voltage source, or into the capacitor. So that will look something like this. So we have 1, 2. We're interested in the delta I out that flows. So this bundle now of 2 wires, V out, V out. And if we apply our delta V out to the first branch, well, we're going to get basically what we had before. That's going to be delta V out divided by RO4 parallel RO8. That's the incremental resistance seen looking into the output of the circuit that we figured out in the last phase of our calculation without the capacitor. And so in that case, we have delta I out 1, 1. So this is delta I out 1, 1. And notice that that current will not excite any current flowing in this other loop in the circuit, which is completely isolated from it, since we split V out into 2 replica sources. And so we'll move on to branch 2, or delta V out here. And now, of course, we're going to get a delta I out 2, 2. Which is current flowing into the capacitor. And we can write that using the idea of the complex impedance of the capacitor as delta V out divided by 1 over j omega C out, where omega is the angular frequency that we're driving at. And this is delta I out 2, 2. And so that 1 over j omega C out will pop upstairs into the numerator, if you like. And we have a number of different ways we could write this, but we can have Z out, the incremental output impedance of the circuit, will be given by RO4 parallel RO8 in parallel with 1 over j omega C out. Okay, so if you factor the delta V out, you get 1 over this parallel combination plus 1 over j omega C out. Move the delta I out downstairs on the right-hand side, move this 1 over this plus 1 over that down here, and we get a triple parallel combination. We can keep this grouped if we like. And we can expand this two-way parallel combination, keeping this one grouped as the product over the sum, and that's going to give us a product, which is RO4 parallel RO8 divided by j omega C out divided by the sum, which is 1 over j omega C out plus RO4 parallel RO8. And we can clear out the nested fraction here by multiplying this 1 over j omega C out through the denominator. And this becomes RO4 parallel RO8 divided by 1 plus j omega RO4 parallel RO8 times C out. And so the gain, so this is Z out. So the gain on node fixing it's going to be a GM times Z out. which is going to be GM1. So here we have an interesting result. If we consider this now, which is a function of frequency, for low frequencies, i.e. for omega much less than this time constant, which is R04 parallel R08 times C out, the magnitude of this imaginary part in the denominator is going to be very small compared to 1, and we can neglect it. And at low frequencies, we're back down to where this reduces down to the differential mode gain that we started out with. We didn't have the capacitor there. But when we get to high frequencies, when omega is, say, much larger than 1 over R04 parallel R08 times C out, then we get an interesting result, which is that we have something that's dropping off inversely with frequency. The gain is dropping inversely with frequency. And so it's basically kind of got a low-pass type characteristic. So at low frequencies, the gain is high. It's about on the order of 100 or several hundred or something like that. And then it kind of has this pole, this normal pole, 1 over 1 plus j omega tau, that hopefully you'll remember from your ISIM days. And the roll-off is 20 dBs per decade once we get past this corner frequency of 1 over R04 parallel R08 times C out. And so the way that this capacitor comes into play is that it doesn't come into play at low frequencies, but when the impedance of the capacitor becomes comparable to the incremental output resistance of the circuit at low frequencies, then that capacitor starts to make a difference, and it starts to reduce the output impedance from its low frequency value, and we wind up with a gain that's starting to fall off with frequency. And so this is the beginning of our consideration of circuit dynamics. Anyway, that's enough for now, and hopefully that'll be enough to get you started to do your lab 9 reasonably well.